Good morning, everybody. Okay, so yesterday we could not record it, and finally it was resolved. There was something to do with the IT section, basically. So I requested them, and then there's uh, some setting was to be changed. So I don't know how it got changed to begin with, but now it's okay. Now we can record it. Okay, so we will be holding these online classes on this link only, which is the original one. Okay. Okay, guys. So the last class we looked at the what we call it the Galerkin method. Okay, so the highlight is from the strong form, we convert that it into a weak form, and then we assume some trial function. Okay, so there's some trial function ux that we assume, and then there is a weight function. Okay, that also we assume, which can be of the same form as ux as long as it satisfies its own boundary conditions. I mean, essential boundary condition. That's what we're talking about. Okay, so and based on that, we do the mathematical analysis, meaning that whatever we have the weak form, we put this trial function there, we put the weight function there, then we say that weight function could be arbitrary, so any coefficient cannot be equal to 0, and this cancels out, basically cancels out, meaning that we take the weight functions out of the equations. The remaining equation gives us the value of coefficients in the trial function. So basically main thing is the coefficients of the trial function that we find out, and that depending on the solution we can depending on the trial function itself, we can either find the exact solution or we find the approximate solution. Okay, so similarly, the what we have solved yesterday, similar manner can be solved for different kind of conditions. Remember that the problems could be different, and you should try different kind of problems. So even a simple problem uh, like this, if you have a force F naught like this one applying here, there is no body force, and then you know that in this case solution will be very easy, right? So solution will be very easy, and you can exact solution will be in this case will be linear. Yeah, so but you can set up problem in this case and you can solve it. Yeah, so all those things are simple problems that you should try yourself. Okay, we will again we will repeat it, we'll revise it more and more, so first let's complete the what we different methods, so earlier Galerkin, the second problem that method, problem not problem but method, what you call it, a Ritz method. Yeah, and this Ritz method is basically different. It is the same thing basically, yeah, but your formulation is different. So how it works like this: if you have a spring, let us say, yeah, and then it is based on an energy formulation, yeah, and if you are from anything to do with energy, it is good to understand based on the some mechanics, so let us say if there is a force, this is spring K, with K spring stiffness, and you are giving a displacement U. Yeah, then there is a if you remember Castigliano theorem that we studied during the solid mechanics course, we have basically the some energy strain energy, right? You have the strain energy, and the total energy there we formulated as potential energy, right? So we call it potential energy. Potential energy is equal to strain energy minus work done. Yeah. So this is the formulation. You can write pi equal to psi minus work done W. You can write like that. Okay, where pi for potential energy, psi for strain energy, W for work done. And potential energy needs to be minimized. So in this case, if you have a spring, simple a spring like this, or you can have a simple a bar which is have a force applied at the end, similar kind of things. Eh? So you have a force applied F, let us say F naught. Both are equivalent, right? You can, as you know that, but the spring is easier. So easier means easier to understand. So we have like this. So how to formulate that? Strain energy in this case will be strain energy of psi is equal to half, as you know, half k u square. Right? This is the strain energy is, right? So that you know already, yeah. Okay, and this you can also have a plot. You can see that if you have a u based on u, right, and then you have a similar force which will be like this, and hence the area under the curve will give you, right, this is what the psi is. Yeah. Okay, now strain energy is given. Now work done. Work done, if not, if u is a small, we are talking about, so work done is equal to W is equal to F naught times u. Yeah. Okay. This we are assuming that suddenly you apply F naught force, and this has moved by u. So this is F naught u. So potential energy formulation is pi is equal to psi minus work done, which is equal to half k u square minus F naught u. So this is how you formulate it. Yeah, and the idea is the pi is minimized. So the structure will work such a way this potential energy is minimum, or that's why this principle also known as the minimum potential energy. Minimum potential energy for formulation. Yeah. Okay, so pi has to be minimized. So d pi over minimized with respect to what? With respect to u. Yeah, so u is the variable there. So d pi over du is equal to d over du, and you have half k u square minus F naught u, which is equal to, if you integrate, differentiate half k to u minus F naught, all others are constants, or will be equal to 0. Why? This is minimized, so that will be equal to 0. And hence, what you get? You get ku minus F naught equal to 0, or you get F naught equal to ku. Right? So this equation you get, and you know that F naught equal to ku is the actual answer, or u you can find from here, u will be equal to F naught over k. So this is the example how it works. Yeah. And this, of course, you have already applied all those things when you studied the Castigliano theorem. It is the same thing. Yeah. But here we are looking at the like big picture. It's not a small picture, it's a big picture. We are looking at the equation from the differential equation perspective. How the formulations can be different for the same problem. And that's we are looking at. Okay, now what happens in case of a a finite element formulation. So like if you have a bar, for example, we're talking about 1D problem only, and if you have the body force Bx, that's we are familiar now. There could be some end force here as well, right? There could be end force here. And there'll be reaction force here as well, so all those, if you are looking at, and how will you find out all those things will be incorporated, somehow has to be incorporated uh, into the equation itself. Yeah, so for this, if you have to write the equation, how will you write it? So let us say you have this force applied, there is another force F naught as well. You can also apply that force at the end, depending on the problem. We are taking an example, and we have to write the formulation for this one. Okay, now how to do it? So first of all, we strain energy. We have to find out the strain energy for this. Strain energy psi is equal to what? So for that, we have to first take one slice here. Okay, so strain energy we have to find out. So just we write here. But for a small slice, if we want to find out the strain energy, or d psi will be equal to what? Will be simply strain times stress times a strain. That's it. Yeah. So how do you write? You will write like this: sigma times d strain. Yeah. That's how you are going to write. Like stress times okay, so let's not d not write, just write here stress times strain times volume, right? Volume, that's the main thing, right? So what is the stress here multiplies by what's the strain? This is the energy per unit volume multiplied by volume, right? That's what that will be. Okay, now what is the stress here? Okay, so stress will be equal to how do you write that? You will write it as sigma, writes sigma, and then strain. So strain multiplied by, okay, multiplied by volume. Volume will be area multiplied by dx. So we have this is as dx. Area, which may be a function of x, all could be a function of x, sigma could be a function of x, epsilon will be a function of x, a could also be a function of x. So this is the strain energy due to this small slice. And then if you want sigma, we have to over the whole domain, we have to integrate a dx. Right? This is what the strain energy is. Yeah, you can expand it further, as you know that this will be nothing but E times epsilon is this is expanded further, right? And then you will have a strain, and then a dx. Yeah, okay. And then when you like integrate it, automatically you will see that it will be so this will be like this. When you integrate, how will it look like? This will look like this. So when you have for a spring, if you have to find out, so if for a spring you have to find out strain energy, how do you do? So you have to be correct about it. So this is what the area that we are referring to. So we will examine whether this is correct or not. Is there any problem there? Okay, so I think it will be half. So we will look at that. Half times stress times strain. So this is if you look at for So this one is a strain, this is a stress, right? So if you are looking at for any point, let us say we are talking about the this is for the whole thing, and here the stress, the in this case this is kx square ku square, you right? But if you have a small bar like this one, and we are looking at this point, at the last point, let us say, yeah. So or any point, because stress or strain will be the same at any point. If you are looking at as you increase the strain, stress will also increase. And for that point, if you have to find out strain energy, that will be how do you write? This will be this area is nothing but half sigma times epsilon. Yeah, so because this is the area we are talking about. So what we wrote here, sigma times we have to also write half there, so should be half. It will be half. Yeah, it will be half times stress times strain multiplied by volume. So this is what it should be. And that's why we get psi is equal to half, and then you have E strain square, area is also there, dx 0 to L. So this is what the strain energy is, and then work done. Okay, now we have to look at the which all forces are working here. So if you say here there is a body force Bx which is being applied, and then there is a force, this force as well applied, right? F equal to F naught. And what is the value of U here? This will be UL. So the work done W will be because of two things. So one is because of this body force. So body force, this will be equal to body force Bx multiplied by U, right? U is a function of X, Ux, and this is the force per unit length, and this is the displacement. Okay, so we have to multiply it by x dx. Okay, so that bx multiplied by dx is the total force at this point, which has u displacement. So total work done will be this much, for because of one small slice for the whole. This we have to integrate, so this becomes like this. Also, there will be a term coming because of this force as well. So we will multiply F naught multiplied by whatever the value of U is at x equal to L. So F naught times U at L. So this is the total force as far as this problem is concerned. For different problem, the work accordingly you have to work out. So in that case, potential energy phi is equal to psi minus work done, and psi in this case will be half EA, right? Now we know that epsilon equal to du over dx, right? So we write du over dx whole square dx, right? So EA, epsilon is du over dx, so a square of that minus these things, right? And we get minus 0, so it will be 0 to L over the whole domain. So 0 to L, and then you have B U dx. Yes, Somnath.
Yeah, actually, sir, I have some doubt, sir.
Yeah.
Sir, U at L, sir. Sir, it is due to body force, or sir, or only for F0 force, sir. This is a I'm little bit confused on that. If of U of L, sir, in the last term, U of L.
Yeah. So this work done is because of F naught only.
Oh, only for F0. Okay, okay, sir. Thank you, sir. Thank you so much.
Yeah. Okay. So then we have 0 to L B times U dx. Yeah, and then you have this is because of the body force, the work done. Then because of the boundary force. Okay, so the difference between two forces are, one is the boundary force, So this is the body force, this is the boundary force. Yeah, so this is acting over the domain. So you can also write omega as to denote the domain or the body, and then you denote this uh, boundary as gamma. You can also write it gamma as which denotes the boundary, and this omega which is the body. So maybe a different color I should have used. So let's say this is green. So the green means the body or the domain, and gamma means boundary. Okay, so difference is F naught is a boundary force. Yeah, F naught is a boundary force, and B is a body force, or this acts on the domain, this acts on the boundary. Yeah, so for both of them you have to find out the work done. Okay, so this will be F naught, and of course where you apply the force F naught, there displacement is U at x equal to L. So accordingly we have to write F naught U at L. So this is what the formulation is. Yeah, and then for solution will be, accordingly you have to find out the solution. How? Here also this is equivalent of our the differential equation, which you called a strong form, and then the weak form you had. This is the potential energy form. Yeah, or you also call it the functional form. So this is a functional. So this is a function of a function is called functional. So this pi as a function of U itself, right? So this is also known as a functional. So this is variational calculus. Basically, this is one of the courses taught in graduate level. So this comes from there. So this is called functional, or simply function of a function. So basically, pi denotes a function which is a function of U, which is given like this one. Okay. Now, what happens is, you say if potential energy, this is also, we know the potential energy, right? So this is the potential energy. Now, so that pi is the minimum, our formulation is what? Del pi is equal to 0, or you say variation of the functional is equal to 0, right? So variation of the functional is 0, or there is no variation at some point. There is the value of function will be the same, basically, because potential energy is the minimum. Meaning what? If this value remains the same, this is like a stationary at some point, right? So it is same as saying the slope becomes 0, right? So variation of the functional is minimum or 0, you can say, right? I'm double quoting it, variation. It's called variational calculus. Anyway, we don't have to delve into those. We understand from the physics point of view, from the solid mechanics point of view, this is a potential energy, and this has to be minimized. How can it be used? You can, let us say, we can take a small example of this. So there is, how can we find out? Yeah. So let us say you have this a bar like this, and then we have to find out, maybe we use the same function as we used earlier, right? So we can also find out the solution. We can compare it. So let us say this is bx equal to b naught that we assumed, and we have to solve this problem, and we know that ux equal to 0 is the boundary condition, and then we have at the other end we have force equal to 0. So we say EA, right, du over dx at x equal to L equal to 0, or simply du over dx at x equal to L equal to 0. Yeah, slope itself is 0 at the end, and we have to find out u. And how to find out? In this case also you can start with the value of ux. You will assume at c0 over c1. Again, it has to satisfy the boundary first. Yeah, so I mean it has boundary condition, and that is 0 equal to c0 plus 0 equal to 0, and to begin with you have to make c0 equal to 0, and that means your equation is form of c1x. Now we have to only problem question is c1 equal to what? That's we have to find out, and we will apply the Ritz method or minimum potential energy method to find it. Yeah, okay. And how do you do it? So we have ux equal to c1x, so du over dx will be equal to c1. Now we put in the potential energy form, so we have pi is equal to, yeah.
Sir, in this case, if we solve the another condition, du by dx equals to 0 at x equals to L.
No, we don't do that. Yeah, so natural boundary condition we don't satisfy. Yeah, u has to satisfy the
Essential boundary
this
condition.
essential boundary condition only.
Okay. Okay.
Got it? Yeah. The other is in the equation, but you does not have to satisfy. If you satisfy, then you have solved the problem already to begin with. No, then what is the need of solving?
Yes.
So yeah, so that's the thing. That's a difficulty also. Approximate solution may not satisfy the natural boundary condition. Yeah. Okay. Now pi is equal to what? First we have psi minus w. So psi, let's find out first. Psi equal to 0 half EA, right? So E is constant, A is constant. Du over dx square and dx 0 to L, right? So half 0 EA is there, and then you have du over dx. Over dx is c1, so we write c1 square, right, dx. So which is equal to half EA c1 square and simply L. So this is what we get as far as the psi is concerned, or the state energy. This is the state energy, total state energy. Now W, how to find out W? W is will be 0 to L, and then you have U, right? B naught times ux is equal to 0 to L. B naught is constant, and u is c1x, right? C1x dx. So we get b naught c1, and then x square over 2, and then L 0. So you can half b naught c1 L square, right? Okay, so this is W. There is no F naught is 0, so F naught here is 0, so there is no work done because of this one, so we will not write anything about that. Yes, automatically this condition is automatically applied. How? There is no work done itself, so there will be no contribution because of that. If you had this equal to some value F naught, then that will appear, right? If you write F naught times jo u at L means C1 L, you have to multiply. Yeah, so those things automatically taken care of. Okay, so you have W equal to this. Now only thing is, now we have to write now in terms of the potential energy, and this potential energy is pi is equal to you have psi minus work done, and then psi we got half EA, then C1 square L, C1 square L minus this value, which is half V naught C1 L square. Yeah. Okay. You have that. Now, only thing is this pi has to be minimum, right? This is the minimum potential energy. And what is the variable here? Now, pi is a function of C1 only, right? So actually, this pi is a function of C1. So we have to minimize the potential energy, and it will minimize with respect to the coefficients. Remember that in all approximate solutions, when we find out an approximate solution, C1 has to be minimized. The coefficient has to be found out. And hence, what will you do here? You will minimize pi in terms of the coefficient itself. So d pi over d C1 is equal to half EA, then 2C1, right? L minus half B naught L squared. Yeah, has to be equal to 0. Right, and then you get from here you get to find out C1, right? So what do you get? You get here, you see here, this is half and half. Will so you have EA times L. So simply you get C1 is equal to B naught L divided by, so B naught L divided by 2 EA. Okay, and that means what? You got the C value. So hence Ux will be equal to C1x is equal to, you have B naught L over 2 EA times x. This is the same value that you obtained when you use some other method. Yeah, when you use the Galerkin method, you got the same value. So that really means, that tells you that both are actually same, because your trial function was same and you get the same value. So at U at L is equal to B naught L square over 2 EA, and you can plot it also now as you did earlier, and the exact solution, as you know from the last class, goes like this, and your this solution will be like this, yeah, and this value is equal to B naught L square over 2 EA. Yeah, the value is L. This is X, this is U. Any question, guys, so far? Any question?
Sir,
Okay.
yeah. Sir, I have a question. Sir, what about if we are taking the higher order value of U? Because in the solution we have to find out the C1 and C2 as our solution. So if we are taking higher orders, then how it would be incorporated in this functional form, because it is in some in some linear form. So the higher order would have to mode C1, C2, C3. So how would we find out that?
Yeah, let's take it up. Let's see how it works. Okay. Yeah, so this is same as any other optimization problem. Even you have one variable, you take the derivative with respect to that variable. When you have more than one, then you take the partial derivative with respect to each coefficient to make equal to 0. So you will have a number of equations.
Okay.
Yeah.
Okay.
Okay. Let's take it up. Okay. Let's solve it. Okay. Now. Okay. So let's now assume higher order system. Now our trial function itself is Ux equal to let's call it C1x plus C2x squared. Let's see whether it works. If that is the thing, then what happens? we have du over dx, right? Which is the strain will be equal to C1 plus 2 C2x, right? Hence, the strain energy will be equal to psi is equal to half EA du over dx square dx, right? 0 to L. And what do we get? Equal to half 0 to L. EA, we can make it outside, and then you have du over dx. So you have C1 plus 2 C2x x square dx, right? Okay, and that will equal to what? That will equal to EA over 2, and then we can write it as C1 plus 2 C2x cube over 3 divided by 2C2, right? We have integrated from L to 0. Is fine? You guys are with me? No? Equal to EA over 2, and then we put the value of L first. So we get C1 plus 2C2L over 6C2 C2 cube of that, right? Minus, right? Minus, we put equal to 0, so we get C1 cube divided by, okay, I think, yeah, we made a mistake here. Cube will be only for these guys, not for this. So should be like this, okay? 6, okay. So you have C1 cube divided by 6C2 again. Yeah, 6C2. Okay, that's it. Okay, so we got psi, so we can write the final form. Psi is equal to, we will take EA over 12 C2. So EA over 12 C2, and then C1 2 C2L, C1 plus 2 C2L square minus, sorry, a cube, so we write cube, minus C1 cube. So we have cube, C1 cube. So this is the psi. Now, what about the work done? Work done is equal to 0 to L bu dx equal to 0 to L b, and then you have C1 plus C2x, sorry, C1, just a minute, C1x plus C2x square, right? And dx is equal to, this is a B naught, so B naught is outside. Then we have C1 L square over 2 simply, plus we have C2 L cube over 3. This is what it will look like. Okay, fine.
Yes, sir.
Okay, now our potential energy pi, which is a function of C1 and C2 now, is equal to, we have EA over 12 C2, right? Okay, 12C2, and then you have C1 plus 2C2L Q minus C1Q minus B naught C1L square over 2 plus C2LQ over 3. So this is the equation. Now remember, this is a little bit complicated. I have written, actually it's possible to get rid of C2. You know that AQ minus BQ formulation, you can automatically C1 minus this will come out, you know, and then you will have C2. So this will have simply C2 will cancel out, you know, so you will have here quadratic term for C1 and C2 here. So it will not be cubic because automatically the C2 will cancel out. So then that becomes easy basically. So you can write now what d pi, so partial derivative d pi over d c1 is equal to 0. So you write the equation, and then you will have d del pi over del c2 equal to 0. So another equation. There are two equations, two variables, c1 and c2. You solve for c1 and c2. Right? Based on that, you can find out C1 equal to what, C2 equal to what, and then you have the solution. Yeah. Okay. So okay. So let's look at that. Okay. So let's simplify. Psi will be equal to EA 12 C2. So EA over 12 C2, and then we will have this minus this. So what is the equation? You remember when you have like AQ minus BQ is equal to A minus B, A square plus AB plus B square. Do you agree? Is this the equation? Anybody remembers? Yes or no, guys? No idea? Okay. This should be what I remember from my high school. Okay. So is this. Okay. So please verify. If not, there this you can also, okay, so you can also solve here basically. Okay, let's do it. Okay. So will be A cube plus A square B.
Yes, sir, it's correct,
Plus
sir.
A square minus B square minus A A square B minus AB square minus BQ, right? So let us see. We get A square B, AB square. So you have AQ minus BQ. So correct. Okay. So similarly, we can write here. So we have this minus this, so this becomes minus this C1, so we get 2C2L, so we write here 2C2L, and then you have A square, then you have these guys, this A square C1 plus 2C2L, C1 2C2L square minus C1 plus 2C2L times C1, right? Plus C1 square. Yeah. So you have C2 here, this will cancel out, and you get here simply okay, just a minute, guys. So this is square terms minus these terms minus this one. This is common. So basically this comes out. So we have EA L over 6, right? EAL and 6 here, this cancels out. So this, and then we can have the whole term here. C1 plus 2 C2L square minus C1 plus 2 C2L C1 plus C1 square. Yeah. So d psi over dC1 will be equal to so you have to work out, guys. Okay, so you understand now. It's now easier to now work with. So you can d psi over dC1, you can take values and so on, you can do. So I have just simplified. So let me not write this, but rather psi, no, pi is equal to the final form that you can use. So EA over 6, EA over 6, EAL over 6, EAL over 6, and then you have a C1 plus 2 C2L, okay, square square minus C1 plus 2 C2L C1 plus C1 square. Yeah. minus you have the value here, B naught C1 L square over 2 C2 L cube over 3 minus B naught C1 L square over 2 plus C2 L cube over 3. So this is the pi now, and now this is the easy to differentiate now, because what you have is you can also expand it. You can expand it and you can get even simpler form for this one, So now it can be done very easily. Yeah, it can also cancel out basically if you see. So okay, why not do that then? Okay, here let's cancel it. Then you have C1, maybe use different color. So we have C1 square plus 4 C1 C2L plus 4 C2 square L square minus C1 square minus 2 C1 C2L, right? Okay, and plus C1 square. Yeah, will be, let's cancel out few things. So we have this we have this cancels out. Then we have this minus C2. So this guys C1 C2L. So we get 2 here. So simply we get C1 square plus 2 C1 C2L plus 4 C2 square L square. Yeah. So even more simplification. So pi is equal to EA over L 6, then C1 square plus 2 C1 C2L plus 4 C2 square L square. Okay, minus B naught C1 L square over 2 plus C2 L cube over 3. Okay, so we have that. Now we can differentiate. So not absolute but partial derivative, because pi is has to minimize. So C1 is equal to EA over 6 to C1 plus 2C2, and this will be 0 because no C1, minus B naught and then L square over 2. So this we get, that has to be equal to 0. Del pi over del C2 is equal to EA L over 6. Then we have 0 term we'll get here. We get here is 2 C1L plus 8 C2L square minus B naught L cube over 3, right, is equal to 0. So we get two equations, right? So equation number 1, equation number 2, and now we have to rearrange them, yeah, in terms of C1 and C2. So we can write it here. C1, C2 is equal to some value here we get. Yeah. So finally, remember that all these approximate solution, finally we get in form of matrix. You know, that is the what the aim is. Yeah. So all these approximate solution work that way. You have the linear system that we build from a differential equation. So that's what the purpose is. So now C1 and C2, if you see here, this that does not have C1 and C2, so this will straight away go to the other side. Yeah, so this will be B naught L square over 2, B naught L cube over 3. So we can write straight away so we have B naught L square over 2, L cube over 3. Okay, because they are going this side. So now here E over 6 is the common, so we can write here. So EA over 6. Okay, done. Now we have C1 and C2. So we have 2 and 2L. 2 to L. Yeah. Okay, so we write here 2 and 2L. 2 and 2L, and here you get 2L 8L square, 2L 8L square, 8L square. So this is the equation that you need to solve. Yeah, and we have 2 common, so we can further reduce it. This becomes 3 here, so equation becomes EA over 3, and then we can write like this. So C1 C2 is equal to, yeah, then let's write 6 is there, right? So you have 2, 2, 2, 8. So we will cut it. We can make it 3 here. This becomes 1. This becomes L. This becomes L. This becomes 4L square, right? Straight away. So we write C1 C2 equal to B naught over 3 B naught over EA. So B naught here, 3 goes from here to here over EA, that side. Okay, and then we have 1 L 4 L square inverse of that. And then we have L square over 2, L cube over 2. So we can even have L square, which is common here. We put it from here, L square. Yeah, and then so that we have here 1 over 2 and L over 3. So this is the solution, right? C1, C2. So let's go further. Final value C1, C2 is equal to 3B naught L square, 3B naught L square over 3A, and how do you invert it? You interchange here, right? And then minus here, right? So you have 4L square minus L minus L1, yeah, and divided by 4L square minus L square is 3L square. We divide by 3L square. So first let us write half L over 3 L over 3 divided by 1 over 3L square. What? This is the determinant of this is 4L square minus L square, 3L square. So we divide by the determinant, so that this multiplied by this is the inverse of the values. So equal to, we get the now this. So we have we have 3L square already here, 3L square. So this takes care of already, and then 3.
Sir, EAL over 6 will be the common.
EA over L.
EAL over 6. Here is
Just a minute. So here we have EA. So let me see here. So it should be EA. I wrote something else. So EA. Yeah, fine. Here should be EA only. And then we had 3B naught L square. So
one L is also there. EAL.
EAL.
Yes.
Where is EAL?
On slide number 16, sir. On at pi, an equation of pi, EAL over 6 is there, sir.
Yeah. So just a minute. In both of them it is like this, right? So we missed here also. Then.
Equation 1. Yes.
Yeah, we missed here. EAL over 6. So EAL has to be there here, right? Okay, fine. So should we like this? Right?
Yes, sir.
It's fine now?
Yes.
Okay, so you can check, guys. So EA over L, it will be like this. So you can also check, you can make a mistake, so you can always check. So what you get here is 3L square. So B naught over EAL is there, and then this one takes care of this, and then we simply multiply this one, yeah. And what do we get? We get like this. So we have 2L square minus, so right here 2L square minus L square over 3, and here what do we get? We get minus L over 2 right? Plus L over 3 is equal to B naught over EAL, and we get 6 minus 1 5 L square over 3, and here you get minus, so we get 6 minus 3L plus 2L. Yeah, so we get equal to B naught over EAL, and 5 L square 5 over 3 L square, and minus L over 6. Yeah, fine. Okay, so this is what you find out, but I suspect there may be some error somewhere, guys. So is equal to C1 times X. So your value is becomes B naught over EA 5 over 3 L square of L times X minus C2 X square. So, and B naught over EA 6 here X square. There is some solution looks like problem because this is not the exact solution. So we made some mistake somewhere, you know, so please check it. Yeah. So we made some mistake. Our solution should be the exact solution that we got yesterday, and it does not look like this is the exact solution. Yeah, so it
Sir,
should be,
we made, I think, mistaken expansion of a cube minus b cube.
yeah, possible.
Yes, sir.
Possible. You check it or let me know. Okay, answer should be like this. Expected answer, because you should get the exact solution. Expected answer. So please you check and report next day. Okay, I mean on Monday. You should get ux equal to you remember we had what was the solution? B naught over EA, B naught L
So b naught L over 2EA into x.
you should get like this, something like this, right? Plus, oh sorry, it should be B naught L x over 2EA and like this. Yeah, so I think it should be this one, this equation. Yeah, or is equal to B naught L to EA x minus B naught over EA two term will not be there probably.
It's only EA, sir.
Only EA. Yeah. So you should get like this. Half P naught EA x square. That means you should get C1 C2 is equal to B naught L EA 1 minus half. Sorry, minus, you should get L So you get L here minus half here. This is what you should get. This is the expected answer. Yeah. So in a step somewhere we made mistake. So please you find out. Okay, you see and you should get the exact solution like this. Yeah. Okay. Any question, guys? Any question? Do you have any question? Okay. So please check it. Please check it, and you make the note. Okay, and you inform me where we made the mistake. Okay. So we'll see you on Monday. Okay. See you guys.
Thank you, sir.